Hello, can you hear me? Yeah. So, good morning and welcome to all participants for the third day and the session 6G of the 6th International Conference on Nanoscience and Nanotechnology at SRM-IST. It is my pleasure to introduce So it is my pleasure and honor to introduce Professor Ashish Kapoor as a session chair. Professor Ashish Kapoor is serving as a professor at the Department of Chemical Engineering at SRM-IST. His research work is on he works on many research areas, which includes transport phenomena, microfluidics for environmental and biomedical applications, membrane technology, biomaterials, modeling, and simulation. Professor Ashish received different awards, such as Best Poster Award at Department of Chemical and Biomolecular Engineering in the year 2010 at UIUC. He also a recipient of Handwriting Travel Award in the year 2010 at UIUC. He is a recipient of Silver Medal at IIT Madras. He is also a recipient of B. Ravichandran Memorial Prize at IIT Madras. With this brief introduction, I would like to invite Professor Ashish to take over the session.
Thank you, Professor, for your kind introduction. So we'll begin our session today. So I hope all of you have been enjoying the last 2 days of the conference, and today we are on the third day. So in this session, we are fortunate to have 2 invited lectures by esteemed speakers from Japan. So first, I would like to introduce Professor Hirokazu Tatsuoka from Department of Engineering, Graduate School of Integrated Science and Technology, Shizuoka University, Japan. Professor has been research interest in the areas including development of new crystal growth systems and simple nanostructure synthesis processes. He has been working in the area of development of new electrical generators. His interests also include synthesis of silicon-based nanosheet bundles for thermoelectric applications and growth of AG nanostructures as antiviral and antimicrobial agents. He has several awards and achievements to his credit. He has been the visiting faculty in Material Science Division of Engineering and Applied Sciences, Caltech, in 2007-2008. He has also been visitor in the Department of Physics, NUS Singapore in 1996, and in Department of Material Science and Metallurgy in University of Cambridge, UK in 1996. He is also been the visiting research fellow at Department of Physics at Durham University in 92-93. So we are looking forward to enlightening lecture from Professor Hirokazu. I request you to please deliver your talk.
Can you hear me?
Yes, sir. We can.
Thank you very much. So thank you for your kind introductions. First of all, I would like to thank to all the organizers to give me a chance to introduce our recent research activities. So thank you so much. So I share my slide. Okay, so I would like to talk about synthesis of these silicide these three sites, so nanomicrostructures by reactive deposition process. So reactive deposition process is very old and traditional technique, but it's still useful to advance nanostructures. So using this reaction deposition technique, so semiconducting silicide so can be formed. This silicide, so from the environmental point of view, so use of safe, abundant material should be considered in futures. So semiconducting silicide have attractive matter additions to be a potential to create environmentally conscious electronics, because this is non-toxic and abundant. So this is an element from the earth crust. So in this materials group, so two kinds of semiconducting silicide are there. So one is two metal silicide, so another one is transition metal silicide. And we also focus on related material like this. So reactive deposition technique is quite simple ones. So the ground layers is resulted by competition of deposited atoms and interdiffusions between the deposited atoms and the atoms from the substrate. And we can control ground phase and mass thickness and some other structures. And this flux ratio can be controlled by vapor pressures. So it's very simple ones. So in another viewpoint, from the application point of view, so since CNT was discovered, self-standing nanowires or nanoseeds have been expected to enhance their functionalities, so in semiconductor technologies. So for example, so the application to the thermoelectric generator and or other lithium-ion battery and applied except for the large size or large volume devices. But however, so it's not easy to handle such a small nano-sized materials to apply such a large-sized devices. So we have been proposed new types of morphologies of nanomaterials. It's like nanosheet bundles. So nanosheet bundle is a collection of nanosheet, large, highly oriented, and well-aligned, dense and tight together. And some examples are drawn like this. So this is ideal ones. So also, so nanosheet bundles on or substrates like this. So this is an example of nanowire bundles we have made. So I explain later. So this is a powder form of nanosheet bundles. And this is also nanosheet bundles on substrate. So thin seed formed on the substrate. So also these nanosheets are exfoliated to each other to become more thinner nano-sized sheet. So any other example of the nanosheet application on the substrate are reported like this. So high density electronic devices, photodetectors, photocatalysts, and energy storage or supercapacitors. So made on this substrate, so using such a nanosheet morphologies. So from this background, so back to the reactive deposition technique. So I would like to introduce the growth technique, so from traditional depositions, and then to make nanosheet bundles. It would be useful large-sided devices I explained now. So this is quite traditional ones. So on the substrate, kept at higher temperatures, so metal atoms are deposited, and the atoms are reacted, atoms from substrate by interdiffusions. The simple growth system is like this. So iron is deposited at low deposition densities. Nano-sized nanorods are formed on the substrate. The structural property was characterized like this. So manganese silicide is also formed by the dot form and thin layer forms by controlling the deposition rate of manganese atoms onto the silicon substrate. So in that case, manganese silicide dot are formed. So under the original substrate surface, it's different from the iron case. So this difference is a difference of dominant diffusion spaces. Iron, silicon for this iron silicon case, manganese for this manganese silicon case. It's quite traditional ones. So I would like to introduce magnesium silicide, formation of magnesium silicide nanorods and wire bundles. So this structure can be applied to the photocrystals. So the silicide, it's not easy to make such structures by a top-down or bottom-up technique. But for silicon is easy material to make such structures. The first, we make this structure silicon, and then after by magnesium depositions, these rods become magnesium silicide. So using this technique, fabrication of silicide nanowire bundles can be formed. This is a silicon nanowire arrays. So using simple chemical reactions using these ones. So after making such structures, so these silicide wire bundles can be formed by thermal annealing with manganese chloride materials and magnesium vapor pressure in the vapors. So we try this wire bundles to the thermoelectric generators in futures. So next, I would like to introduce magnesium silicide nanosheet bundles formations. So to make a silicide nanosheet bundle structures, so we use calcium disilicide as a template materials. This calcium silicide has such a crystal structures. This is hexagonal, and along the C directions, layers are alternatively stacked. So calcium layers, silicon layer, calcium layer, silicon layers. And there are some polymorph exist. So if we can calcium layer, if we can extract calcium layer only, so we can make silicon nanosheet, silicon sheet. So this is a case of the formation of the calcium disilicide domains, so on silicon substrate. So and this layer is along the C planes. So in that case, C plane is formed, so the inclined, so with a silicon surface, or like this, like this, like this. So this C plane is on stand, so on the silicon surface. So by extract calcium layers from the compound, so we use IP6 phytic acid to extract calcium. So this material has a chelate characteristics, strongly bind to the metal atoms. Then we remove calcium atoms only from the silicide. So this is the domain structures of calcium silicide. So after calcium extractions, so this domain structure remains, and in the domains such as layer bundles are formed. So and then the layer is stand on the surface, not parallel to the substrate surface, is nearly perpendicular to the substrate surface. Sorry. So this is a TEM observation of the bundles. So sheets are easily exfoliated to each other to make more thinner layers. So from structure characterizations, it's confirmed it is silicon and very thin layers, because so such a spots, it's very special for the thin silicon layers. And for the cross-sectional view, so it is interesting to remain the original calcium silicide structures even after calcium are extracted. So this is the original CA site template. So even though calcium atoms remain extracted, such a layered structures are still remains. So please keep in mind 1 nanometer, about 1 nanometer periodic structures still remain along the C-axis. So this is a photoluminescence spectrum of the nanosheet bundles. So this is a silicon. This is a expected or experimental or energy gap for the silicon nanosheet thin layers in the literatures. So our material has a 1 nanometer thickness, has about a 2 electron energy gap. So we observe this luminescence nearly about 2 electron volt. So we discuss this luminescence. It's caused by the periodic structures of the silicon nanosheet originally from the CASI2 template. So then, we extract calcium and make silicon nanosheet. So then we add magnesium atoms into the silicon sheet. So using these materials. So for the growth process, substrate with calcium silicide and magnesium compound is placed in this glass container and put into the vacuum chambers. Then thermally annealed about 600 degrees C and 2 hours. And we characterize like using this technique. So this is some images after magnesium silicide nanosheet are formed. So the shape is roughly strained or distorted, but still a domain structure remains. So layered structure is still remains. So this is before reactions CaSi2 domain structures. This is after treatment, magnesium silicide nanosheet. It looks one sheet is very thick, but these sheets are easily exfoliated each other to become more thinner layers. So this is a TEM image from the substrate. So this is magnesium silicide sheet. So from the TEM observations, so it is confirmed this is magnesium silicide. And it's interesting. So these spots come from these pattern, lattice fringes is not bulk features. This pattern is elongated. These pattern is elongated these directions, and the new spot. So these feature prove this sheet is very thin. So these feature appears by tilting the sample. So compared to the electron beam directions. So this is also a cross-sectional view. And for these materials, it is also such 1 nanometer periodic structure remains in the magnesium silicide. So magnesium silicide, so originally don't have such a long period structures. So this is Raman spectrals. So this red line is peak energies observed for bulk case. So this one is from the magnesium silicide nanosheet. Its peak is shifted and the tail is a little bit tailed. So it's suggested, so the phonon structure is changed by forming the nanosheet structures compared with bulk materials. This is a photoluminescence spectra of the magnesium silicide nanosheet bundles. So this is a luminescence from silicon substrate, and some peaks still observed even these samples. So these peaks are already known from the surface oxide layers or MgO materials remained. So, but new peak appears for these materials. But we discussed this peak is originated is also such a nanostructures. So future investigation will be required to prove these discussions. So in conclusions, so silicide films, nanostructures are synthesized by such a simple reactive deposition technique. Morphological and structural controls on resulted products are possible. So with preferable choice of source and template materials. So further development of the growth technique will be expected to synthesize more sophisticated structures with functional surface. So thank you for your attention. So it will be nice to, this conference will be our, this conference will be the first step for our future collaborations. Well, thank you very much.
Thank you, Professor, for your very informative lecture. Now we leave the session open for questions from the audience.
Yeah, yes, Professor. Thanks for the nice talk. I have a few questions. Professor, do you hear me?
Yes, yes, please.
Yeah, how do you control the oxidation of silicides? Because it is a form of silicon, basically.
Sorry, how do I control?
Yeah, of the oxidation. It get oxidized,
Oxidation.
right? Yeah.
Oh, okay. Yeah. Yes, oxidation is very, very important. So always I'm struggling with oxidations. So one thing is the reaction in a high vacuum, but still not enough. For structural characterizations, so the oxidation are not so affect the characteristics. But as a next step, we need to characterize electric properties. So the oxidation is much affect these properties. So we need to avoid it. So now I try this phenomena occur in liquid phase. We try now in liquid phase to avoid excitations.
What is the, I can't get it, Professor. What is that phase?
In liquid, melt. As an next research, I try in melt, in liquid.
Oh, okay. And the measurements also made in situ measurements? The characterization.
In situ measurement?
Yeah.
So, sorry again.
So the characterizations which you made,
Sorry again.
all are the characterization methods, if you follow the PL and other characteristics, so which are in situ measurements? In situ measurements?
In situ.
Yeah.
Not in situ measurement.
Yeah.
Not in situ measurement. I don't have such a equipment. For characterizations, TM, PL, Ramans, and then I try to characterize electrical property, for example, and ZBEC and thermal conductivity, and so on.
Yeah, okay.
I also, in future, I would like to characterize catalytic properties in future.
Yes, yeah, I'm particularly interested in that because this band gap is very suitable for that catalytic process. That is why I want to know how do you control the oxidation. It is silicon is very favorable to have oxidation immediately when you expose to this atmosphere. So it will affect the catalytic properties.
Yes.
If it is in the same form like a magnesium silicide or a manganese silicide, that will be fine. And I feel that, that's what my first question, that how you can control the oxidation for these materials. is I feel it is very difficult.
Thank you. Thank you very much for your very important suggestion and point.
Yeah, and one more thing that I want to ask you,
yes.
Professor.
Yes.
Yeah, I want to ask you one more question. Is this magnesium silicide and manganese silicide, you have taken the precursors like separately and then you reacted before deposition, or you combined the source materials and did the evaporation?
You are asking about the pre-treatment of the deposition?
Yes.
So,
the source materials are
yes.
The source materials are mixed.
Source material just
yeah. They mixed before the deposition.
Source material, yes, mixed. Yes, mixed.
Yeah.
Yes. So the source materials. So usually we use powder form.
Yes, powder form. Yeah.
So we bought it, and without no special treatment, and placed in a vacuum. Yes.
Yeah. May I know what are the source materials for magnesium silicide?
No, especially no.
No. What are the sources that you used for depositing magnesium silicide?
Magnesium. For magnesium, so magnesium ball, a metallic ball. Magnesium
Metallic
ball,
ball, just
and
a pure metallic
magnesium
ball.
chloride.
Okay.
Yes, and magnesium ball. Sorry, magnesium chloride powders.
Okay. And for silicide, Professor?
Yes.
For silicide source, just you use the silica?
Silicide source. So we use calcium silicide as a source of silicones.
Okay. Thank you, Professor.
Thank you, sir.
Oh, thank you.
Yeah. Due to interest of time, we have to just restrict our questions session to a few minutes. Now we'll move on to the next invited talk. I take great honor in inviting Professor Takayuki Nakano, whose research interests include development of novel optical functional devices using polar structure of group 3 nitrides, development of neutron imaging sensors, and chemical reaction and process system engineering, semiconductors, optical and atomic physics, electrical and electronic material engineering. Professor, you are most welcome to share your insights with us.
Thank you, Chair, for introducing my presentation. Just a moment. Can you see?
Yes, sir, please.
Just a moment. Okay. So, good morning, everyone. My name is Takayuki Nakano from Shizuoka University in Japan. Today, I'll talk about development of double polarity selective area growth using metal organic vapor phase epitaxy for publication.
Sorry for the interruption. Can you please maximize your screen?
Screen?
Full screen mode, yeah.
Just a moment. Okay.
Yeah, thank you. Thank you very much.
Okay. So, first of all, let me introduce the Sorry. So, today's I'll talk about this title. First of all, let me introduce the topics related to the gallium nitride properties. As you already know, GaN is direct transition and the wide gap semiconductor materials for the optoelectronic devices. Moreover, other property is high saturation electron velocity and fracture endurance for high power electron device. From these properties, gallium nitride is the material which had much possibility, and many research had been done on gallium nitride. Especially the research is carried out in recently various attention points. Then we carried out the research from the viewpoint of the polarity structures. Next, let me introduce the topic related to the polarity of gallium nitride. One of large difference from other conventional semiconductor like silicon is the stable structure is ultralight. This is ultralight crystal structure. And the presence of the lattice polarity, which is coming from the lack of the inversion symmetry along C-axis. Features of each polarity consist like here. Gallium polarity surface is very flatness morphology and very much chemical stabilized. Nitrogen polarity surface is formed hexagonal facet and not more stable than the gallium polarity surface. Band gap and reflectivity are same in both polarity surface, but the nonlinear optics constant is reversed. Moreover, the profile of surface potential consists like this figure. There is large possibility on the device using the polarity because the characteristic is greatly variable in the polarity like this. So using the different symbol of second order nonlinear susceptibility, phase matching crystal can be fabricated by arranging each polar gallium nitride periodically. This schematic image is SH device using gallium nitride QPM crystal. As shown in this figure, the light transmitted through the QPM crystal emits short wavelength laser light due to the second harmonic generation. Many papers reported, and two report paper is shown on here. Satisfying QPM condition, SHG devices are fabricated and mixed up with aluminum nitride. SHG device included deep UV is applied. So this slide shows the fabrication method for GaN QPM crystals. Upper part shows fabrication process on the other laboratories. After growing on the aluminum nitride buffer layer, QPM crystals are fabricated by dry etching and gallium nitride rigorous process. So this method requires two epitaxial growth processes. Furthermore, mass productivity is low because the MV method is used. Therefore, we proposed a process that can be produced in a single growth using the MOVP method. MOVP method is excellent mass productivity. The proposed process is the double polarity selective area growth MOVP process, which is a selective area growth process using a carbon mask. By using this process, the fabrication of double polarity substrate is succeed. However, the reproductivity is low by the air exposure process. Therefore, we made further improvement and built the improved DP sub process. In this slide, I explain our improved DP sub process. First, carbon mask was patterned on cyprian sapphire. Then we put the sample on the chamber, and the temperature was raised. Hydrogen cleaning was treated for gallium polar gallium nitride on unmasked polygon. Temperature was falling to low temperature buffer layer for gallium polar. Then temperature was raised to grow gallium initial layer. After growth, gallium initial layer to fabricated nitrogen polar gallium nitride. Ammonia cleaning was treated. Temperature was fallen to low temperature buffer layer for nitrogen polar. Then temperature was raised. After rising temperature, each polar gallium nitride buffer layer was grown. Then the double polarity selective area growth was treated. So our proposing process called double polarity selective area growth, DP-SAG. DP-SAG has feature using carbon mask, and the merit of using carbon mask is creating by lift-off process. Removing carbon mask using ammonia cleaning and need just only one-time growth process. Growth condition is shown on here. Growth pressure was 30.3 kilopascal. 5-3 ratio was about 10,000. Ammonia flow rate was 1,000 SCCM. Gross temperature was 1,050 degrees C. Gallium source was trimethyl gallium, and nitrogen source was ammonia. Using evaluation method is SEM, AFM, KFM, XRD, and photoluminescence. First, we studied the DP-SAG growth mechanism. This schematic shows the interfacial formation mechanism in DP-SAG. In this case, lateral growth of nitrogen polar with high growth rate is enhanced. The step flow growth of gallium polar is prevented because of the growth of nitrogen polar over the facet of gallium pora. Therefore, this spread the gradual interface region between surface of different polarity. Next, growth rate of gallium polar facet is promoted, and the lateral growth rate of nitrogen polar is inhibited. Nitrogen polar growth along the facet of gallium polar gallium nitride. Therefore, it's possible to fabricate DP sub with an abrupt interface. The growth rate for each polarity gallium nitride could be controlled by manipulating growth condition. To fabricate DP sub with an abrupt interface, we investigated the dependence on the 5:3 ratio. This slide shows the dependence of 5:3 ratio in 200 micrometer pitch DP sub gallium nitride. The 5:3 ratio was varied between 6,800 and 11,900. This shows cross-sectional SEM, bird view SEM image at the polarity interface for each 5:3 ratio. As a result, the growth rate of each polarity was confirmed to change the 5:3 ratio. And a remarkable difference in growth rate was observed in the nitrogen polar. This slide shows dependent of 20 micrometer pitch DP sub. Since we found some conditions at 200 micrometer, we conducted a detailed study at a pitch of 20 micrometer. When we investigate the 5:3 ratio dependence, we obtained the relationship shown here. Furthermore, by growing under condition where the growth rate ratio was close to 1, we succeeded in producing crystals as shown here. From this result, we understand that it's possible to fabricate QPM crystal with abrupt heterointerface by optimizing the 5:3 ratio and controlling the growth rate ratio of each polarity. Next, we try to fabricate gallium nitride QPM crystal for UV SHG. On this slide, I'm talking about problems and proposals. On last slide, I talked that we have achieved fabricating 20 micrometer pitch pattern DP gun, but for ultraviolet SHG device, DP gun with narrow pitch pattern around from 2 to 4 micrometer pitch pattern is necessary. In 4 micrometer pitch pattern, we confirm the problem that growth condition of 4 micrometer pitch pattern is different from 20 micrometer pitch pattern. In this study, we attempt understanding growth mechanism and fabricating of narrow pitch pattern DP gun for UV SHG device. In this slide, I'm talking about examination of DP sub on the early step. Following to AFM image of gallium initial layer, gallium polar region was fabricated on unmasked region, and no layer was grown on curved mask region. Following to AFM image of each polar buffer layer, we confirmed that growth of each polar buffer layer for DP GAN was succeed. From this slide, these results indicate that fabrication of DP GAN buffer layer was achieved by optimized growth condition. On this slide, I'm talking about DP sag at low 5-3 ratio condition. We fabricated DP GAN grown with 5-3 ratio 9600. Following to the surface SEM image before KOH etching, DP GAN with different periodically surface morphology was fabricated. Following the surface SEM image after KOH etching, DP GAN was etched periodically. Following cross-sectional SEM image, SEM image, DP GAN with abrupt interface between each polar region. Following to this slide, we achieved fabrication of DP GAN with periodical polar arrangement of 4 micrometer pitch pattern. Next, I'm talking about DP sag at high 5-3 ratio 11,300. This 5-3 ratio was optimized growth condition of 20 micrometer pitch pattern DP GAN. So DP GAN was fabricated at this condition. Following to surface SEM image, each polar region was confirmed, and surface SEM image after KOH etching, DP GAN was etched periodically. As you can see, AFM image before KOH etching shows that gallium polar region was covered by nitrogen polar gallium nitride lateral overgrowth. And AFM image after KOH etching shows that nitrogen polar region was etched. This sample schematic image is shown on here. This result indicates that nitrogen polar gallium nitride growth rate is faster than gallium polar gallium nitride growth rate. This result indicates that optimal growth condition in 20 micrometer pitch pattern is different from 4 micrometer pitch pattern one. So next, I'm talking about DP GAN evaluation. About evaluation of DP GAN were carried out. This graph shows the relationship between 5-3 ratio and each polar gallium nitride growth rate ratio in each pitch pattern. Following to the graph, at high 5-3 ratio, nitrogen polar gallium nitride growth rate is faster than gallium polar gallium nitride growth rate. And low 5-3 ratio condition, gallium polar gallium nitride growth rate is faster than nitrogen polar gallium nitride growth rate. And nitrogen polar growth rate in 4 micrometer pitch pattern is faster than 20 micrometer pitch pattern one. So this discussion is going to be talked to the next slide. And from PL measurement, growth condition around 5-3 ratio 9,000 is best condition for DP gun. Each polarity growth rate is nearly equal in 5-3 ratio around 9,000. So in this slide, I'm talking about discussion using surface diffusion of gallium.
You have another 2 minutes for talk and another remaining 3 minutes for discussion.
Sorry. So diffusion length on gallium polar region is longer than diffusion length on nitrogen polar region. In wide pitch pattern, some source transfer from gallium polar region to nitrogen polar region, and many sources stay on the each polar region. Source concentration time is over.
For discussion, time is for discussion. Maybe you can wind up in 1 minute. We can go for remaining 2 minutes for the question session. Yeah.
Okay. I just this slide is skip. So this slide is very important. So on this slide, on this slide, optical measurement result. So Maker fringe for optical measurement was used. So this graph shows Maker fringe measurement result through SHG SHG peak. This peak means grating number is 3 peak. So this figure shows the relationship between incident energy and peak intensity. So SHG light intensity is proportional to the square of fundamental wavelength intensity. This result and this one is theory and experimental data relationship between SHG light intensity and grating order number. So this result indicates that optical measurement using fabricated GaN QPM crystal suggests the expansion of SHG. So this one is last slide. Spectral measurement result for SHG MQPM equals 3. So SHG peak is peak confirmed near the 390 nanometer. So incidents are indicated the realization of wavelength conversion. Summary is this is summary, and finally, I would like to thank you, my colleague, for supporting this research. Thank you for kind attention.
Thank you, Professor. We have time for one question from the audience, please.
Yeah. Yes, Professor.
Yeah.
What is the main application for this dual polarity gallium nitride structures? Because we had several applications for gallium nitride. And what is the main application that is suitable for this dual polarity kind of growth?
So real target is next step is aluminum gallium nitride. Aluminum nitride QPM crystal emitted to 205 50 nanometer SHG laser. We use next
next step.
Next Blu-ray disc. So CD, compact disc, DVD, Blu-ray. Next UV disc. We want to next.
But already it was existing, right? With a single polarity aluminum gallium nitride.
Yeah. So only single polarity aluminum gallium nitride.
Yeah, it's already existing in the commercial also. But I want to know what is the benefit to go into the dual polarity.
Sorry.
What is the benefit to move into the dual polarity?
So single quality argon laser is very difficult. Maybe we want to use this QPM crystal and blue laser is high power UV laser is will be fabricated.
Thank you, Professor.
Thank you, sir. Now we move on to the second part of the session. We have contributory lectures. The first one that we have in the sequence is CL112. H. Manas Singh, are you there? Is a paper on the electrical parameters. H. Manas Singh and P. Chinnamuthi.
Yeah, hello, sir. Am I audible?
Yeah, so please confine your talk to about 7 to 8 minutes so that we can have some discussion.
Yes, sir. Just share my slides. Good morning, one and all. My name is H. Manas Singh, research scholar from Department of AC and IT Nagaland, carrying out work under the guidance of Dr. P. Chinnamuthi. In today's presentation, the title is Electrical Parameters in AG Germanium Nanowire Silicon Metal Semiconductor Device as a Function of Frequency and Voltage. So this is a brief outline of the presentation. So with the development in the semiconductor industry, currently we are at a level where the scaling down on the devices is becoming an issue. So in this context, since the past few decades, researchers and scientists alike are looking at new materials or alternate materials which can help in solving this issue. So in this context, germanium, amongst other materials like gallium arsenide, gives advantage in few parameters like the carrier mobility, like hole mobility, electron or relative carrier charge mobilities are higher, as well as the dielectric constant is high. So in this research work, the choice material is germanium. So the motivation behind the decision to synthesize 1D structure is that 1D structure, as we can see in this figure, 1C, in comparison with the bulk form as well in the quantum plane or quantum dot, there are certain advantages it offers in this kind of structure. The first advantage is that with 1D structures, we can achieve a larger surface to volume ratio compared to the other three forms, and as well as in 1D structure, the movement of electron is confined in only one direction. The electrons or charge carriers are free to move in only one direction, and in the other two planes, it's not. It's confined. And moreover, if we achieve 1D structure, we can have enhanced optical path length within the structure itself, as represented in figure 2. So the synthesis technique employed in the work is glancing angle deposition technique, which is incorporated into an electron beam evaporator. So this GLAD technique is an extension of OAD, oblique angle deposition technique. Some of the features or the advantage GLAD offers OAD is that vertically aligned nanowires or nanorods can be achieved easily in comparison with other techniques. And also the porosity of the film can be controlled by varying the incident angle of the vapor flux. And the third advantage is that due to the self-alignment effect, which is due to shadowing effect, we can achieve a vertical nanowire as shown here. And also this technique, GLAD technique, is a simple technique compared to other prominent CVD and PVD technique, as well as it is a catalyst-free technique. So this is the experimental, this is the apparatus e-beam evaporator system, wherein the insert you see, we find the chamber where the deposition takes place. The deposition is carried out in a high vacuum pressure level, and then the mechanism as to how we can achieve vertical nanowire is that the incoming vapor flux after the source has been evaporated, what happens is that we can divide it into two components, vector components. One is the perpendicular component and the other one is the parallel component. So since in the GLAD technique, we are rotating our substrate, right? So due to the rotation, what happens is that the parallel components gets cancelled out, and effectively we are left with the perpendicular component. Hence, due to which we can achieve perpendicular nanowires comparatively easily with other techniques. So in the discussion, we have carried out the capacitance and conductance analysis using KITLI 4200 SCS. So if we look at figure 7a, we can see that the capacitance has been carried out from 200 kilohertz to 2 megahertz. So in this frequency range, we observe that with this kind of a device structure, there is a decrease in the capacitance value as we increase our frequency. This is primarily speculated to be because of the presence of series resistance as well as surface states or interface state densities. Moreover, we can see that there is a dispersion in the depletion region as indicated here by the cursor. This is also primarily because of the surface states present in the device structure. This is the schematic of the device. So also from the conductance study, we can see that it's on contrary to the capacitance plot, we see that as we increase the frequency, the conductance value increases. This is attributed to the increase in polarization, and with increase in polarization, there is an increase in the carriers at the metal semiconductor junction. So in order to further understand the role played by the series resistance and this interface state densities, we have calculated the series resistance and DIT using this thing, Nicolin-Druce method and Hill-Coleman method. So according to the series resistance plot, we see that as we increase our frequency, the resistance value decreases, and whereas in DIT, this is a surface and interface state densities, it decreases as we increase our frequency. But also, moreover, we can observe that at certain frequency, there are two peaks at around 300 and 300 kilohertz and 900 kilohertz. The presence of peak denotes that denotes the presence of different types of surface interface density states. Like we have fast trap states and slow trap states. So, and also the decrease in DIT with increase in frequency is because as the frequency is increased, these surface states cannot follow the AC signal at higher frequency. The response time by these defect states is not able to respond if we increase to the applied AC signal if we increase the frequency. But at lower frequency, it has the necessary time to respond to the change in the AC signal. So it can be conveyed that in the device, the excess capacitance offered at the lower frequencies due to the presence of DIT, and at the higher, as we move on to this thing, higher frequency, the capacitance, there is a major role played by the series resistance. And also, we try to calculate the we corrected capacitance by considering the resistance, series resistance offered by the proposed structure. So, and if we look at the graph here, we have done a series of comparison both in capacitance and conductance with measured capacitance, and we have found that while considering the effect of series resistance, there is a slight increase in the capacitance and conductance in both the cases. This, and furthermore, we can see in our
times up. You have to finish it up.
Okay, yeah, sir, yes, 1 minute. This due to the presence of charge transfer at the interface, and this is the structural image wherein we found that the height is around 152 nanometer and the width around 52 nanometers. The Gaussian plot agrees with our estimated diameters. So in conclusion, we were able to synthesize germanium nanowire using GLAD technique in E-beam evaporator, and then we also like to conclude that this device is dependent on both frequency and voltage. Also, the presence of DIT and series resistance is established, and also we also established that DIT is effective in inversion region at low frequency and series resistance in high frequency at the accumulation region. And also that peak in the corrected conductance infers that there's a charge transfer at the interface. I would like to acknowledge IIT Durgapur for the characterization facility.
It's okay.
These are some of the references. Thank you.
Yeah, thank you, Manas. The session is open for question.
Yeah, what is the glancing angle deposition? How did you do that?
Yes, sir. The GLAD is an extension of oblique angle deposition technique, sir.
How did you find the angle? First of all, how did you find the angle that
yes,
that angle is used to the glancing angle? By using
extra
D?
See, no, which angle, sir?
The glancing angle that you want to say that at some particular angle the nano rods are growing, right? The deposition takes place at a particular angle. How did you find that angle initially?
Yes, sir. There are a series of paper established that in this technique, if we set the angle of incidence of the vapor flux, as shown in figure here, if we maintain the alpha angle greater than 80 degree, we can achieve nanowires or nanorods effectively. But at 85, the probability of achieving this thing, proper nanowires with
sir,
good porosity.
My question is, how do you fix this 85 degree? Is there you follow just from the literature? You follow from the literature, or you?
It has been established. No, yes, it has been established through experimental verification.
Okay, thank you.
In our lab setup, we experimentally determine, if you can see here, this is where the substrates are held. We have to.
That is okay, but my question is different. That how you could first find what is the angle that you want to keep.
Yes, sir. That has been established through experimental work in the literature, sir.
Yeah. Okay. Thank you.
Our GLAD technique. Yes, sir.
Okay. Thank you, Manas. Now I invite the next speaker, Ms. Lakshmi. Lakshmi Kumari.
Hello. Can I audible, please?
Yeah, please share your screen.
Okay, fine. Sir, can I start? Are visible my PPT?
Yeah, please go ahead.
Okay. Good morning, everyone. I am Lakshmi Kumari. I am a research scholar in Department of Physics, IIT ICONN-2021, India. Today, I am going to talk on the topic role of PVA capping on photophysical property of chemically prepared cadmium sulfide nanomaterials, insights on energy transfer mechanism in CAP system. So what is the motivation and scope here? I have chosen this material cadmium sulfide, which is a second-6 semiconductor nanomaterial, and it has a direct band gap 2.42 electron volt, and it has high electroluminescence capability, and it also enhances photoluminescence conductivity. So it is a very attractive. It has very attractive property to be utilized in optoelectronic application. And cadmium sulfide exhibit both cubic and zinc blended structure. But we wanted to achieve some tunability and enhancement in PL. So we have capped here with polyvinyl alcohol, which is an insulating polymer. And through literature survey, we have we have gotten this idea. It has enhances PL intensity due to passivation of both non-radiative and radiative surface traps of this nanomaterial, and it also enhances its optical properties, so it can be leading candidate for light emitting application. So we have synthesized this material by using chemical co-precipitation method. Here I have for the preparation of pure cadmium sulfide, I have chosen an appropriate amount, that is 0.5 molarity of cadmium acetate and dissolved in distilled water. And after that, it is placed on a stirrer for stirring sometimes, and then an aqueous solution of sodium sulfide is added on this cadmium acetate solution, and then both the sample are mixed sample are stirred for some times, and after that resultant precipitate was filtered with washed and washed with ethanol and distilled water several times. Finally, the precipitate at vacuum oven dried at 100 degrees centigrade for 10 hours and collected in powder form of CDS nano powder. For capping, I have done same process. Just I have added some amount of appropriate amount of polyvinyl alcohol for capping just before centrifuging it, and these are the compound, and these are the amount which I have added here. Sorry, yeah, sorry, sir. These are the amount which I have added 0 gram and 0.1 and 0.2 gram for, and these are the sample code which I have used for the samples for further analysis. After preparing powder form, in powder form, we have studied its crystallinity property, and from XRD we can see here the crystallinity increases with capping of PBA in CDS, and also these XRD pattern agree well with hexagonal CDS nanostructure. CDS structure of diffraction text which I have mentioned here, and crystallized size are found to be 16 and 9 for pure and capping system, and all have tensile strain, and lattice parameter has been also calculated, which is mentioned here. After that, we have studied its microstructural property, and from microstructure we can see that all samples have roughly irregular agglomerated particles in cluster form, and there are some agglomeration enhances after capping. And also we can see the particle size somehow it decreases after capping. So for getting more insight behind how what amount of particle sizes decreases, we have also plotted its histogram plot, and we can see histogram or exhibit almost symmetric distribution of value of diameter around their mean value, and all samples have almost similar, but their average diameter and standard deviation varies, which I have mentioned here. And also we can see now we can see that the diameter of nanoparticles are found to decrease with capping of PBA. After that, we have studied its optical property by absorption spectroscopy. From absorption spectra, we can see for pure sample, the absorption peak at 471, and after capping PVA, the absorption spectra is slightly shifted and gaining more enhanced visible absorption. And also we have plotted top plot, and from this we get band gap of nanomaterials are found to decrease with capping, and it varies from 2.3 to within 2.4, which I have mentioned in next slide. So as we have seen in our absorption spectra, the PBA capped system achieve more visible absorption. So here we have find Urbic energy For finding aerobic energy, we have plotted variations of ln alpha function as a function of photon energy, and the linear portion gives the slope, and aerobic energy is calculated by taking inverse of this linear slope, And from figure we can see the increase in aerobic tail energy, which I have also mentioned in the table. And here I have also given the value of band gap. So we can say that after capping there are somehow they are generating in disorder and also defect level within the crystal lattice, which is the main reason of increasing aerobic energy. So getting more insight behind the defects level and disorders in series lattice after capping, we have studied its photoluminescence property. And from photoluminescence property, we can see we have excited this material with an excitation wavelength of 350 nanometer. And from photoluminescence property, we can see there are no change in peak position and also width. Almost they have similar in all samples, but there are more enhancement in overall PL intensity. And also the broad band can be attributed to broad size distribution of particles and trap recombination, which I have also seen in histogram plot of this material. And also enhanced luminescence signify minimization of surface defect and enhancement of electron hole recombination. And after capping, defect state are almost modified, which signify there are the tunability in their luminescence and enhancement in PL intensity may be due to the reason of freight and charge transfer, which may play a vital role in this nanomaterial, which we will study in our further study. And after that, we have plotted its chromicity analysis. From chromicity diagram, we can see their chromicity diagram shifted color coordinate toward
Lakshmi
white
Kumari,
region.
we have to wind up soon.
Yes, sir.
In a minute. Yeah.
Okay, sir. The photometric parametry of this parameter show the utilization of this material in optoelectronics applications. So after getting more enhancement in PL intensity and tunability, it increases us to study its electroluminescence property. So here we have plotted external power efficiency along with voltage, and insights signify the variation of internal and external power efficiency. And here phi shows the injected charge carrier within our material. So these are the values which I have got from this, and all these study are calculated by theoretical consideration. And after that, here I conclude. After capping, crystallinity increases and also nanoparticles diameter decreased, and after capping, more visible absorption enhances, and PLS spectra shows in there are some chances of rate and charge transfer after capping, and also for tuning luminescence property and efficiency of light emitting diode by using this nanomaterial. PB and series, both physical and chemical interaction between the capping agent and series nanoparticle must be taken into consideration and further optimization. So here I acknowledge. I'm thankful to my professor,
Please,
my
yeah.
supervisor, Professor
Yeah.
Ekekar. I'm thankful
Please wind
to
up.
CRF. Yes,
Yeah.
sir. Just
Yeah.
1 second, sir. I'm thankful to CRF and Physics Department of IIT ISM Dhanbad for research facility. I'm thankful to IIT ISM Dhanbad for financial
Yeah. Yes.
support. I'm
Yes.
thankful
Okay.
to ICON to 2020 organizers. Okay, sir. Thank you.
Yeah.
Thank you for listening. Yes, sir.
Okay, thank you for the presentation. We have time for one question.
So why you are choosing PVA for your capping? And I have
Sir,
series of questions. You tell me why you are choosing PVA for capping?
yes, sir. Actually, I wanted to changes some in. I wanted to suppress some intrinsic defects which is
Okay.
visible in series, and that's
Intrinsic
why.
defect which is present in the surface.
Yeah, sir. Actually, there are so many defects: interstitial sulfur, interstitial cadmium, and vacancies of sulfur. Due to this, we cannot achieve the tunability in our visible emission. And also, I wanted to achieve some more visible absorption, which I have seen in my absorption spectra. So I wanted to use this in ultimately in light emitting application.
Yeah,
That's
works
why I
fine.
want.
Okay, your particle difference between these composition is not much difference, crystal size, and
Yes.
you are just capping that, and but you are finding the huge difference in the absorption. What is the reason for that? What you are?
Sir,
What is your
actually,
explanation about that?
yes, sir. Actually, I have not studied in more detail, but here from this data, I can conclude that after capping, there are so much modification in their surface defect, which is present in their surface. So it attract more light towards inside it, and it absorb more absorption light. This may be the main reason, I think.
Okay. Okay, fine. Thank you very much.
Thank you, sir.
Okay, so now we will move on to the last contributing lecture for this session. Ms. Anandita.
Am I audible?
Can you increase your volume?
Yeah, just a sec. So, sir, am I audible now?
Yes, yes. Please start.
So let me share my screen. Okay. So, good afternoon all. I am Anindita Rekha, currently pursuing my PhD from Saha Institute of Nuclear Physics, Kolkata. And my today's talk is on emergence of ripple morphology on silicon surface at off-normal incidence via ion beam assisted surfactant sputtering. So here goes the outline of my talk. First, I'll give a brief introduction on nano patterning via ion beam sputtering, and which will be followed by my experimental work. So the periodic patterns we observed in nature, such as the ripples we observe in the desert, or the water ripples, or the ripples that are formed by the clouds in the sky, they have fascinated our humankind from time to time. And if such macroscopic patterns can be generated in nanoscale dimension, and then they have a huge range of applications in the field of nanoscience and nanotechnology. And some of the nanoscale patterns are the nanoripples, nanodots, and nanomers that are generated on a silicon sample. And these are some of the applications. Pattern formation, they can modify various electronic, chemical, as well as optical properties of the solid surface. They can also be used as templates to go various order thin film. Also, they can be used in various optoelectronic devices as well as data storing devices. So, in this regard, to achieve such nano patterns, ion beam sputtering has been considered as a has been considered as a potent bottom-up, uh, potent top-down approach, which is the fine ability to generate various pattern surfaces in a large area scale within a very small span of time. Also, there is no need of any marks or chemicals, and moreover, we can precisely tune various kinds of nano patterns by simply varying the processing parameters. So, coming to my experimental work, this is the schematic of the low energy ion beam instrument we have employed to generate such kind of nano patterns on various surfaces. So the heart of the instrument, that is the ion beam source, is a RF ion beam source, and moreover the whole system is operated by a computer interfacing software. So these are my experimental parameters. Here I have used a silicon 100 p-type substrate as my sample, and as a surfactant material or co-sputtering sample, I have used the stainless steel target. Moreover, we have used argon.
Sorry for the interruption. Is it a surfactant material or substrate material?
The stainless steel is the surfactant material, and silicon is the that is the substrate is the silicon. Okay, so the ion beam that is used to bombard the sample is the argon ion beam of energy 500 eV. So the argon ion beam that it is used to bombard the surface, that is the silicon as well as the co-sputtering material, at an incidence angle of 30 degree. So these are the morphological analysis of my sample. Actually, I have done the morphological investigation at 2 different regions. That is, here you can see one near the surfactant material and other far away from the surfactant material. So the region that is far away from the surfactant material, that is region A, that is 3 millimeter away from the stainless steel target material. Here we observed that with an increase in ion fluence, some nanodots splitted over the surface. And for the highest ion fluence, it is observed that there is a transition from nanodot to nano ripple like surface. And also in region B, that is the region that is near to the surfactant material, that is a stainless steel target material. Here we observe that the nano ripples that are evolve on the surface with the increasing ion fluence. The nano ripples become more ordered as well as the periodicity increases, and for the highest value of fluence, the ripple becomes more pronounced. This is the PSG diagram, that is the power spectral density function of extracted from the AFM images, and this is for the region A and region B. And here we observe that in region A, a small peak is observed for the highest value of fluence, which indicates the emergence of ripple on the surface that we have also seen from the AFM images. And also in region B, it is observed that the that is the peak of the power spectral density function, it becomes more pronounced, which indicates a higher value of ripple periodicity and ripple ordering. Also, we have studied the compositional characterization by performing X-ray photoelectron spectroscopy analysis. Here also we observed that here the blue line, that is, it indicates a pristine silicon surface, and the red line, it indicates the silicon surface that is irradiated at the highest value of fluence. And here we observed that for the irradiated surface, apart from the other elements, the presence of iron and chromium can be clearly observed, and that is due to the co-deposition of the surfactant material from the stainless steel target on the silicon surface. And this is the atomic concentration of various elements on the silicon sample. Also, we have performed a co-level express analysis for the highest value of fluence. Here we observed that here from the iron 3p core level, here we observed that the presence of iron silicide bond can be clearly observed, and which is the main region, that is, which is the vital region for this appearance of such patterns on the on such a surface, because if we don't add any kind of surfactant material, then that is, if we consider a impurity free patterning, then at such incidence angle, that is at such at 30 degree or less than 45 degree of incidence angle, we don't observe any kind of pattern on the surface. But when we add some this kind of surfactant material, due to the formation of this silicide bond, that is this stable silicide bond, the emergence of such kind of pattern can be observed on the surface. Also, we have observed
last 1 minute.
Yeah, fine. Also, we have observed the TAM analysis, and here also the TAM, from the TAM analysis also, the presence of the silicide bond can be clearly observed. Here the lattice spacing, it corresponds to the interplanar spacing of iron silicide, and also from the high angle annular dark field image also, we observed the presence of iron silicide iron silicide from the ripples. And also here we can see that the ripples, it is composed of a silicon, but there is a layer of iron over the silicon surface. So these are my conclusions. So here we can say that surfactant material play a very crucial role in case of nanopatterns on silicon surface. And also the direction of the direction of the ripple that are evolved on the surface, that depends on both the direction of ion beam as well as the co-spotted material. Also the co-deposition of metal impurity, it doesn't have a direct impact on pattern formation, but the formation of the silicide bond plays the main role. Okay, so these are my references. Thank you.
Can you Hello.
Yeah.
Yeah.
So can you go to your XPS slide?
Yeah, sure.
So what if in the blue and red one, what the oxygen one is I think there is a huge difference in the intensity. Is there?
Yeah.
What is the reason?
Yeah, the reason is that the blue one is a pristine silicon, right? But in case the upper one, the red one is a irradiated silicon, and
Okay.
irradiated means that is bombarded by the argon ion, right? So most of the native oxide layer that is present on the silicon surface that is removed during bombardment. So that's why the intensity is less.
So can you go to your ion and AFM image with respect to ion intensity?
Okay. Yeah. I think this one.
So what is the reason for this kind of wavy formation? What is the physical mechanism, or yeah, this
Means
you're
wavy
changing
formation
from the part, yeah,
from dots to this
from
ripples.
particle to, yeah.
Okay. So what we observed that this dots they evolve only at the regions that is far away from the surfactant material target, right? So at this point the concentration of the surfactant material is very less, but this for the region B, that is the surface that is near to the surfactant material, here the concentration of the impurity level is very high.
Okay, thank you.
Okay. Yeah, thank you.
Okay, thank you. So we come to the conclusion of this session. So thanks to all the participants. So we had two introductory invited lectures, one by Professor Hirokazu, who gave us the insights into the synthesis of semiconducting silicides. He introduced us to the advanced reactive deposition techniques for the synthesis of nanostructured materials. And the second invited lecture was by Professor Takayuki, who gave a talk on the development of double polarity selective area growth using MOVP. And this was followed by three excellent contributed lectures from the research scholars who shared their very interesting topics on the research with us. So I thank you all for your kind participation in this. So please continue to join our other lectures in the ICONN. And thanks and have a nice day.
So on behalf of the organizing committee, I would like to thank once again Professor Ashish for sharing this session. Thank you very much.